In this video, we're going to implement A-star pathfinding in Unity Dots. We're going to implement the algorithm in a pure data-oriented way, which will allow us to benefit from the extreme performance of Unity Dots. Let's begin! Okay, so in this video, we want to implement A-star using a data-oriented design. We want to benefit from massive performance from Unity Dots by using the job system and the burst compiler. Now previously, I covered how to do A-star where we made it the normal way using objects. If you haven't seen it yet, then go watch that video. In there, I cover the algorithm in more detail, step by step. Here I'm going to do an overview of the algorithm and then start implementing it in Unity Dots, paying close attention to how we can convert from object-oriented into data-oriented. So before we get to the code, let's first check out the theory. The goal of the A-star pathfinding algorithm is to search to find a path from A to B. So the algorithm already detects walkable and unwalkable areas and correctly identifies the shortest path from A to B. Our map will be grid-based. From each grid position, we can move in all 8 directions. On each node, essentially we have 3 values. First, we have the G cost, that is the walking cost from the start node. So for example, to go from this node into this node, it has a cost of 1. And we can also move diagonally, so from this node into this node has a cost of 1.4. Now, in order for our code to work with ints instead of floats, we're simply going to multiply our values by 10. So horizontally, we have a cost of 10 and diagonally a cost of 14. Then we have the H cost. This is the heuristic cost to reach our final goal. So it's essentially an estimate to try to reach the goal. Our calculation is simply assuming there are no walls, so moving straight towards our goal. So in here, our H cost will calculate going from here to here to here. Again, this is just a basic guess to figure out which nodes to prioritize. And finally, we have the F, which is simply G plus H. So this combines our actual cost from the start, combined with an estimate to reach the goal, and we have our final number. Using this, we can prioritize nodes with lower Fs since those are more likely to be closer to the goal. The algorithm finally stops when our current node is our goal node. So if we start here, first we check all the neighbors. These are unwalkable, so they are ignored. So he checks this one, then checks these 2 neighbors. Then this one has a lower F value, so it checks this one, checks the neighbors for that one. Then it starts locating that one, and it says that this one is the goal, so we have our path. So here, as you can see, the G cost is constantly increasing, and the F cost is constantly decreasing. Then our path is traced back from the final node into our origin node. So each node also knows what the previous path node was. Then for the algorithm to work, we also have 2 lists for our nodes, the open list and the closed list. The open list is where we have all the nodes that are queued up for searching, and the closed list are all the nodes that have already been searched. So we keep going until we find the current node on the open list, or our open list is empty, so we no longer have anywhere to search, so there's no path. Okay, so now that we've looked at the algorithm, let's implement it. Again, in this video, we're focused on the Unity Dots specific implementation, which means data-oriented and no objects. So make sure to watch that other video first, which will make the data-oriented version much easier to follow. I've also made a video covering the differences between reference types and value types. That is one of the main differences between the object-oriented way and the data-oriented way. Objects are reference types, whereas here we're going to use structs, which are value types. So watch that video to see how they behave differently. This video is made possible thanks to these awesome supporters. Go to patreon.com/unitycodemonkey to get some perks and help keep the videos free for everyone. Let's begin by making our script. So a new C# script and just call it pathfinding. And just for testing, let's make a empty game object and attach our script onto it. Okay. Now the core of our pathfinding is to store some data on each grid position. So let's begin by defining our path node. Now, first of all, this will be a struct and call it path node. Now inside, the first thing we're going to need is the position. So let's have an int for the x and an int for the y. And now, since we're working with structs and not objects, that means we're going to work a lot with indexes. So let's also store a public int for the index. Then we have the standard A-star pathfinding values. So we have the G cost, H cost, and F cost. The G cost is the actual move cost from the start node onto this node. The H cost is the estimated cost from this node onto the end node. And the F cost is simply G plus H. Then we're also going to have a simple boolean for is walkable. And lastly, in order to calculate our path back from the end node, then we need to know where we came from. Now in the object-oriented way, here we would just store our previous path node, but we cannot use objects, so instead we're going to define it as our index. So this is the index of the node previous to this one when we're calculating our path. Alright, so here we have our path node defined purely using value types. So that means we can use this struct inside a burst compiled job. Now up here, let's make a testing function. So a simple called find path. We're going to find a path and we're going to receive an int2 for the starting position and an int2 for the end position. Now the int2 is inside the new unity.mathematics library, and there it is. So in here, let's start off by creating our grid. Let's start off with just a basic 4x4 grid. And in order to store our grid, we're going to use a flat native array. Okay, so we define our flat native array, and then since we're dealing with native arrays, we must remember to dispose of them. So at the end, we call dispose. All right, now to initialize it, in here we construct a new path node. And now to set the starting value. So we set the x to this x. Same thing for the y. Okay. Now to initialize the remaining values, we're going to need the index. So let's make a function to calculate that. Here it is, very simple. We just convert a x and y position into a flat index. So in here we can set the path node.index to be our calculate index, and we pass in the x and the y. Then we need to initialize our costs. So first of all, for the path node.gCost, this is the cost from the start node onto this node. So let's start off with all of them at max value. Now for the hCost, which is the heuristic cost in order to reach the end node. So we're going to make a function to calculate that. Now we need to define the weight for the diagonal and the straight move costs. So let's go up here to define that. All right, so here's our function to calculate a distance cost from A to B. And now up here we can set our hCost. It will be calculate our distance cost from position A, which will be this one. So an into with this x and this y. Then the B position will be the end position. So there's the hCost, and now for the path node.fCost, we can calculate this inside of our struct. So in here, let's make a function. And the fCost is simply the gCost plus the hCost. And up here, we simply calculate that. All right. So lastly, we just need the isWalkable. For that one, let's make them all walkable. So path node.isWalkable, let's set it to true. And lastly, we have the came from node index, which we're going to use -1 as our invalid value. All right, so here we have our path node correctly set up. Now, after it's set up, then we need to assign it to the index position in our flat array. So in the path node array, on the index of this index, then we set this path node. Okay, so here we have our grid completely set up. Now, after doing that, let's grab our start node. To grab that, we calculate the index, and up here we use our start position. So this is our start node, and for starters, we're going to update the gCost. Since it's a start, we're going to set it off to 0, and then we need to recalculate the fCost. And again, always remember that here we are working with value types, so what we're doing in here is simply modifying the copy. We're not modifying what is actually inside of this array. So after we modify it, let's place it back in the array. All right, there it is. Now, following our algorithm, we're going to need an open list and a closed list. And again, we're working with structs, so let's define our arrays as lists of int indexes instead of references. And again, make sure we dispose. To start, we're going to start with the start node on the open list. So open list, and we add the start node index. And now while we have nodes on the open list, so while the open list.length is bigger than 0, we're going to grab our current path node. And the current one won't be the one with the lowest f cost. So down here, let's make that function. So here it is. We take our open list and then receive our flat array of our path nodes. Then we do a symbol cycle. So we cycle through the open list, which again contains indexes and not references. So we go through that one, then we access the path node array on that index. And if the f cost of this one is lower than this one, then this one becomes the new lowest. So there it is, very simple. This returns the lowest cost f node index. So in here we simply use it, we pass in the open list and the path node array. Alright, now here we have the index for the node that we want to test. Let's also grab the current node. Now we test if this current node is the final node, then we have reached our destination. So in order to do that, we can calculate the index of our end position node. So we calculate the end node index using our end position x and y, okay? And then down here, if the current node index is the same as the end node index, then we have reached our destination. And we simply break out of the cycle. If we haven't reached our destination, then the first thing we do is remove the current node from the open list. So here we cycle through the open list, which again is a list of integers for our indexes. Then we check if we have the current node index, and if so, then we remove it from the list on that position. Alright, so after we do that, then we need to add this list into the closed list. So simply close list and we add this index. And now here, following our algorithm, we need something else. So we need to cycle through all the neighbors of this current node. So for that, let's go up here in order to define an array for all of the neighbor offsets. Alright, so here we have our array with all of our neighbor offsets. So left, right, up, down, left, up, right, down, and right, up. So we create this native array, and again, always remember to dispose of it. Now in here, let's cycle through the offsets. So we grab the neighbor offset, then we create a neighbor position, which is based on the current node plus the neighbor offset. And now we need to validate this position. So we need to know if this neighbor position is inside of our grid. Let's make a function to do that. Okay, so we have a simple function, testing if it's above 0 and under the actual width and height. So here, as we're cycling through the neighbors, if this position, we test the neighbor position. If it is not inside the grid, then we simply continue. So we continue on to the next neighbor offset. And now if not, then we have a valid neighbor position. Now here, let's check if the closed list contains this index. So let's also calculate the int for the neighbor index. So if the closed list already contains this neighbor node index, then we already searched this one, so we continue. If not, then let's check if the node is walkable. If the node is not walkable, then we continue. And finally, if we go through all of these, then we have a valid node. So here, let's do our algorithm. Alright, so first we calculate the tentative g cost. So that is based on the current node g cost plus the distant cost from the current node onto this neighbor position. If that new g cost is under the current g cost, then we want to update this neighbor node. So we update the came from index to be the current node index. We update the g cost, we calculate the f cost. And again, here we're working with structs. So after we update our node, we need to place it back in the array. So we do that and then we add it onto our open list. Alright, so just like this, over here we have our pathfinding algorithm. And now after doing this cycle, one of two things happened. Either we found a path or we didn't find a path. So the way we know that is by looking at the end node. So we grab a path node for the end node, which will be the path node array of the end node index. And we test if the end node dot came from node index. If it is -1, then we did not find a path. And if not, then we did find a path. Now let's make a function to build our path. So if we have a -1, then we're going to return a empty native list. So our int2 is going to be our path position. And if we have found a path, then we need to walk backwards to get our actual path. Alright, so there it is. We do a while, we have a came from node index in our current node. We grab the node in that index, and we add that position into our path, and finally we return the path. Alright, so just like this, we have our path being calculated. Now it's actually inverted, but we'll worry about that when we make a unit actually follow the path. So up here, if we find a path, let's calculate it. And right now we don't care about getting the path back, we just want to calculate it, so after getting it, let's just dispose of it. And here at the end, again, make sure you dispose of the native arrays that you create. Alright, so here we have our A* algorithm implemented solely using value types. So that means that this is usable with Burst and the job system. But now let's first make sure it actually works. So for that, let's make a test. All the way up here, we are working with a simple amount of behavior, so let's make our start function. And on start, let's simply try to find a path. Our grid is of size 4 by 4. So let's try to find a path from 0, 0 onto, let's say, 3, 1. And down here, when we calculate a path, let's make a debug log so we make sure that the path is correct. Alright, that should do it. Let's test. And yep, there you go. Over here in the console, we can see that we have our path being correctly calculated. Again, it's backwards, but the path is correct. So we go from 0, 0 to 1, 0, so to the right, to 2, 1, so diagonal up, and to 3, 1 to the right. Alright, so the algorithm appears to be working. Now let's add some blockable areas to test it. So in our pathfinding, in here we are creating our grid. So after we do that, let's make some blockable areas. Alright, so here we have some code adding some walls. I just implemented this setIsWalkable function. As you can see down here, we simply set our boolean to either true or false. And up here, we first grab the node on that position, so this one on 1, 0. We set isWalkable to false, and then we update the node back in our path node array. So we're setting a wall on 1, 0, 1, 1, and 1, 2. So essentially we got a vertical wall right next to the start. Alright, let's test. And yep, there we have our path correctly going from start to finish without going through the walls. Awesome! So now that our algorithm is fully working, let's make a bigger grid and do a simple performance test. Okay, so here I added a simple performance test. So we have a grid size of 20 by 20. And we're calculating the path from 00 to 1919, and we're calculating that path 5 times. Then we're simply looking into the logs in order to see the time in milliseconds. But before we run this, let's try it out on the pathfinding that we did previously using objects. Okay, so here I am in that other project. Here we have our pathfinding working with our pathnode class. So as you can see, we're using a bunch of reference types in here. And for the test, we're doing the same thing. So calculating the path from 00 to 1919, on a grid of 20 by 20, and we're calculating that path 5 times. Alright, so let's test. Okay, so here we are, and there we have the result, about 700 milliseconds. Now obviously what I have implemented here has not been optimized at all. This is the most straightforward implementation of the A* algorithm using objects. You can implement pathfinding with object-oriented code and get significantly faster results with just a little bit of optimization. But still, let's take this as our baseline. So here we're taking 700 milliseconds. And now let's do the exact same test with our data-oriented version. And yep, there it is. Over here you can already see quite a big improvement, going from 700 milliseconds down to just 1. So here we have this code running on the main thread, calculating 5 paths one after the other. Now let's put this code inside a job to make it multi-threaded. So we're going to implement all of this in our job struct. So we just implement iJob. And now here inside the execute method, we're going to have essentially the contents of our findPath function. And with jobs, our execute method does not have any parameters, so we need to receive the parameters out here as fields. Okay, there it is, no errors, everything's working great, all right. So now up here, let's instantiate the job. All right, so here we have the same thing. We define the start at 00, the end at 1919. We define the job and then we run it. All right, so let's test. Okay, so here we are, and yep, we still have the exact same results. That's because we're running the job on the main thread and it's not yet multi-threaded. In order to make this multi-threaded, instead of run, we need to call schedule, and we need to schedule all the jobs and then complete them all. Alright, so here it is. We define an array of job handles. We cycle through our 5, we schedule all 5 jobs, and then we tell them all to complete. Alright, so fun, let's test. And yep, there it is. Now it's indeed multi-threaded, and it's taking 0.5 to 0.9 milliseconds instead of the usual 1.2 to 1.3. And now there is still one massive improvement that we can do, which is we can enable the burst compiler. So up here, using unity.burst. And now down here on our job, now since we already wrote all of our code thinking about the limitations of burst, all we really need to do is add the burst compile attribute. And yep, there it is. This is all it takes. However, here we did use one thing that is not supported on burst, which is only in here on the neighbor offsets. We cannot use an into array inside of burst, so let's just easily change this. Alright, so there it is, very simple. And again, everything else has already been made with burst in mind. So our struct only uses value types and everything should work perfectly. Alright, so let's finally test our massive improvement. And yep, there you go, we have our burst being finally compiled, and look at that, we have 0.05 milliseconds. So there is the insane improvement you get by combining all of the dots stack. So with the normal, unoptimized, object-oriented pathfinding, we had this action take 700 milliseconds, and using dots with the job system and burst, we have it working in 0.08 milliseconds. So even without doing any further special optimizations, we already have some insane speed. So here for an insane test, I made the grid 100 by 100, so again going from 0 to 99.99, and we're doing 50 jobs. So this means that we're running 50 pathfinding jobs on the exact same frame. So let's see how long this takes. And yep, there's the answer. 50 units, all searching for the path on the exact same frame, and it's taking 2 to 5 milliseconds. So here we have the profiler. Now let's look at a frame where we're calculating a path. So let's look at one of these spikes. And yep, over here we have a frame where we're working on all of our jobs. And yep, look at that, all of these jobs being scheduled and executed using burst. And down here, look at all the job threads. And yep, there you go, look at all of them, all completely very busy. So we have tons of jobs, all of them working in parallel. So here you can see the insane performance gains you can get by using the Unity .stack. Okay, so here we have implemented our super fast pathfinding algorithm using Unity dots with the job system and the burst compiler. Now this video is already very long, so I'll leave it here for now, but I will cover using the pathfinding combined with the entity component system in the next video. We're going to set up all the components and build a system that will run our pathfinding job and store the resulting path in a component so that the entity can follow it. I'll also optimize this code to see just how far we can push this. So if you're watching this in the future, check the links in the description. And if not, then hopefully that video will be out by next week. This video is made possible thanks to these awesome supporters. Go to patreon.com/unitycodemonkey to get some perks and help keep the videos free for everyone. As always, you can download the project files and utilities from unitycodemonkey.com. Subscribe to the channel for more Unity tutorials, post any questions you have in the comments, and I'll see you next time.